Hello, everyone. Today we're going to look at biconditional, our next compound statement. But first, let's make a truth table. The biconditional has something to do with the conditional, and it's illustrated in the do now. So make a truth table for this compound statement, if P then Q, and if Q then P. Note that this is the conjunction of a conditional and its converse. So let's see what that truth table would yield. Okay, so to make this truth table, we start with a P and a Q, and we'll look at if P then Q, then its converse, and then finally we put those last two columns together and look at the truth values to get the truth values of the conjunction of the conditional and its converse. So, again, the P column always begins with true, true, false, false. The Q is true, false, true, false. Now, a conditional is false when its antecedent is true and its consequent is false. So this would give us false, but the others would just be true. When we look at the converse and Q is the antecedent, then we notice that here Q is true and then P is false, so this would be false here. Otherwise, the conditional is true. And then we know that a conjunction it's very hard to make true. Both conjuncts must be true. So the only place where both conjuncts are true are here and here. So this is true, otherwise, and the last one's true. Otherwise, the conjunction is false. So in the do now, this statement, the conjunction of a conditional and its converse, is called a biconditional. Let's define it. Definition. A biconditional, and again, that prefix bi means two, so we have two conditionals, is the conjunction of a conditional and its converse. And so symbolically, we could write it this way. We could write it as we did in the do now, if P then Q, and if Q then P. So let's write the words here. If P then Q, and if Q then P. And that's a little bit wordy. So there's another way to write this. And we say P if and only if Q. So it doesn't seem like they're synonymous, but they are. P if and only if Q. And sometimes in math, we use that if and only if so much that we write IFF. You'll see a lot of teachers do that. But P if and only if Q means if P then Q and if Q then P. And the symbol for that, if and only if, in logic is written this way. P, if and only if, it's a conditional with two arrowheads. So it's a conditional going this way and the conditional going that way. P if and only if Q. But it just looks like a double-headed arrow. I think that's how you would describe it. And we read this as P if and only if Q. Now, in the do now, we've just proven a theorem. So here I could write I could extend this and write P if and only if Q. These two are the same. They are equivalent. So I'll just recopy the truth table. True, true, false, false. And we have now a truth table for the biconditional. And we can't axiomize this because we use the two axioms. The axiom for when a conditional is true and when it's false, and the axiom when a conjunction is true and when it's false. And we obtained the truth table for the biconditional. And notice that the biconditional is true. So let's look at this now. And I'll do this in yellow because it's the only color I didn't use. The biconditional is true when P and Q are both true and both false. Otherwise, if P and Q have different truth values, the biconditional is false. Notice P here is true, Q is false. Here, P here is false and Q is true. So this we will write as a theorem on the next page. And remember, a theorem is a statement that can be proven true using previous definitions and axioms and other theorems. So the theorem we proved is that a biconditional P if and only if Q is true when P and Q have the same truth values. In other words, if P and Q are both true or if P and Q are both false. And by the way, we can call one an antecedent and the other consequent because they work in both ways. Otherwise, the biconditional is false. And if we wanted to make a compound truth table for the biconditional, we would write the following. P, Q, P if and only if Q. So that truth table would look like true, true, false, false, true, false, true, false. And when P and Q are both true, the biconditional is true. When P and Q are both false, the biconditional is true. Otherwise, the biconditional is false. Let's take a look at a few problems on your worksheet number 17, but I will rewrite them here just in case you don't have that worksheet. All right, and this is exercise number 1. P represents roses are red, Q represents violets are blue, W represents sugar is sweet. So let's write the following in words. Q if and only if, not W. So here we have violets are blue, if and only if sugar is not sweet, because we have the negation of W. Okay, so this if and only if we can abbreviate as IFF. In G, we would have roses are red, either, and actually let's put the word either so it implies that they go together. Either roses, let me just make this correct grammatically. I erased the problem. This is a problem. Okay, G, P, or Q. So we would say either roses are red or sugar is sweet, if and only if, and I'll put IFF here, if and only if violets are blue. And then in the last one, we could say roses are red, and only if both, okay, both, and again, this both would imply that they go together. So we need parentheses. Both violets are blue and again we have the negation of W. And sugar is not sweet. Okay, I think that takes care of translation. Now let's go the other way, from words to symbols. Okay, now these are on your sheet. You don't need to copy them, but I put them down here anyway so you could see them in front of you. 2C says, 10th graders do not take foreign language and do not take art, if and only if they are taking 2 sciences. And we're using the letters F for 10th graders that take foreign language, A for 10th graders that take art, and T for the taking 2 sciences. So let's take it a bit at a time. Notice that the if and only if is here. So I'll put that here. Now we have to figure out what goes on each side. 10th graders do not take foreign language. So that's negated because we have the not. So I will negate F and do not take art and not A. Okay, so I assume that is the first part of the biconditional. The 10th graders do not take foreign language and do not take art. So be careful with the connectives. If and only if they are taking 2 sciences. Well, that's just T. So that would be my translation. All right, sometimes the biconditional doesn't have if and only if, and it's in the form of a conditional, the conjunction of a conditional and its converse, like in 2G. If yogurt prices rise, then the cost of living goes up. And if the cost of living goes up, then yogurt prices will rise. So clearly we have the conjunction of a conditional and its converse. So it would be if yogurt prices rise, then the cost of living goes up. And if the cost of living goes up, then yogurt prices will rise. But again, by definition, this is a biconditional. And in mathematics, we could write it as Y if and only if C. Yogurt prices will rise if and only if the cost of living goes up. And in the next one, and I have to read it to make sure I copied it correctly, it's a long one. It is the conjunction of a conditional and its converse. Let's look at it. If Fred has French toast for breakfast, so there's your if. Or if he has crunchy munchies. Okay, so we've got 2 ifs. Perhaps we could condense that into one if. Then, so perhaps we could say, if Fred has French toast for breakfast or he has crunchy munchies, then it is Saturday or he is flying out of town, and if it is Saturday or he's flying out of town, okay, so there's your other if, or he's flying out of town, then Fred has French toast and crunchy munchies for breakfast. So let's take it slowly. So we've got an if then. So if Fred has French toast for breakfast or crunchy munchies, I'll put that there. Then it is Saturday. So that's Saturday. Or he's flying out of town. I'll put O here because that's out of town. Okay, so that implies the first conditional. and. So this is the first conjunct of the entire conjunction. And notice that, that's quite complicated. And if it is Saturday, or he's flying out of town. Wait, am I doing this right? Or if he said, or he's flying out of town, then Fred has French toast and crunchy munchies. Now, wait a second. Is that and or? Yeah, the first one is or. Yeah, I double check this. This one's or. And the second one, because sometimes we copy and or, I get them mixed up. And the second one is and. So I would definitely write this. Perhaps the author of this problem meant to write or. Yeah, I would tend to think that, but I'm going to leave it the way it is. Yeah, I'm just double checking it here in my notes. I'm going to leave it the way it is, and that would be the direct translation. Notice how important it is to have brackets and parentheses in this last one. So, as far as the biconditional is concerned, is the biconditional commutative? A conditional is not logically equivalent to its converse, but is a biconditional logically equivalent to I can't call this the converse of the biconditional, but can we just say P if and only if Q? Is it logically equivalent to Q if and only if P? And our tendency would be to say yes. Because notice that when both P and Q are true, or when both are false, when we flip the order, they're still true and true here. True if and only if true implies true, and false if and only if false implies true, whether we switch the P or Q. And then if we switch the T and the F, the biconditional is still false. So we can say that P if and only if Q is logically equivalent to Q if and only if P, and a biconditional is commutative. So for extra credit, I'd like you to prove or disprove whether or not is a biconditional associative. Okay, that's extra credit. And that is to say, if P if and only if Q, if and only if R, is that logically equivalent to P if and only if Q if and only if R, when we shift the parentheses. So I'll leave that up to you. There's also something else very special about the biconditional. Let's make a truth table and we'll discuss it. Let's make a truth table for the following. The negation of P, the negation of the conditional P, if P then Q, if and only if P and not Q. Okay, so let's practice making a heading for the biconditional. And this is problem number 5 on your sheet. And it says, make a truth table for the following biconditional. Okay, and in this one, well, I haven't included every connective. The only connective I did not include is or, but we could assign that through the homework. All right, so let's build up this truth table. So we always start with your simple statements, and I only have 2 of them. Okay. And then we'll build the left side. So I have if P, then Q goes first. And then we'll negate that column. Then I'll put a not Q column, which could have been done earlier, but it's okay. And we'll do P and not Q. And then take a look at these 2 columns and form the biconditional. Okay. And remember, we have true, true, false, false. Let's all do it this way so our truth tables are the same. True, false, true, false. And pause the video and take a minute and fill in the chart. All right, so I filled in the first few columns. Again, a conditional is false when the antecedent is true and the consequent is false. So I have a false here. And in the next column, I just negated this. So I have false, true, false, false. I took the negation of Q, false, true, and then I formed the conjunction of P and not Q, and I noticed that P and not Q are both true in this row. Notice true and true. Otherwise, the conjunction's false. Now, let's take a look at the biconditional. So when we take a look at these 2 columns that I put an arrow, notice that they have matching truth values. So this biconditional is always true. This, and if you recall in the previous video, a statement that's always true is called a tautology. But there's something special about this tautology. Notice that in the last video, we said that the negation of a conditional would be when its antecedent is true and its consequent is false. That is P and not Q. And we could see that these are logically equivalent. This is how we prove logically equivalent statements. So it would make sense to say that when 2 statements are logically equivalent, then the biconditional formed between them is a tautology. And if you think about that, logically equivalent statements have the same truth values, and when we form a biconditional between them, that biconditional will always be true. So let's summarize on the next page. So we could say that the negation of a conditional is logically equivalent to P and not Q. But the tautology is not the negation of if P then Q, if and only if P and not Q. All right. Now, there's a very, very big difference between logically equivalent and tautology. Notice the symbols almost look alike, and this is deliberate. This is deliberate. But the logically equivalent symbol looks like an equal sign. So when we say 2 statements are logically equivalent, we're talking about 2 statements. But with a biconditional, we're talking about 1 statement. That's a tautology. And here we really need parentheses because we can't tell which side to look at. Whereas with an equal sign, you know the left side is the left side and the right side is the right side. So in that case, we know a lot of tautologies. For instance, we proved that the double negation of P is logically equivalent to P. Well, a tautology would be the double negation of P if and only if P. We have De Morgan's laws. The negation of P and Q is logically equivalent to the negation of P or negation of Q. A tautology would be the negation of P and Q if and only if, and then I'll put parentheses, not P or not Q. This is a tautology as well. We already proved the logical equivalence, so the tautology comes right out. And then finally, the other part of De Morgan's laws, the negation of a disjunction is logically equivalent to not P and not Q, the conjunction of the negation of each piece. And we have a tautology, the negation of P or Q, if and only if not P and not Q. So let's write that down. This is a very important idea that I'd like you to keep in mind. So when two statements are logically equivalent, which means that they have the same truth values in the truth table, they match, then the corresponding biconditional will be a tautology. Okay, so I'm going to outline that. That's really important. But remember, when we have logically equivalent statements, we have two separate sides, whereas a biconditional is one very complex statement. There's another logically equivalent statement I completely forgot. A conditional is logically equivalent to what other conditional? It's contrapositive. So a corresponding tautology there would be if P then Q, I put that in parentheses, if and only if, in parentheses, if not Q, then not P. Okay, so these are all tautologies. Now, in logic, sometimes we write our laws in this way. We don't write them as a conditional, but sometimes we write them vertically. For instance, we could write De Morgan's laws instead of saying this statement up here. I'm not going to rewrite it. The negation of P and Q is logically equivalent to the negation of P or the negation of Q. We could rewrite it as follows. We write one side up here, draw a line, which means conclusion, and then the conclusion below. So if we're given the negation of a conjunction, then it follows that this is true. Okay, so sometimes we list them vertically to make it easier. In the same way, we could write this rule as follows. The negation of, let me put that in blue here. So the negation of P or Q, if we're given that, then, okay, so after the horizontal line is the conclusion. This is the conclusion. Not P and not Q. And then, of course, the law of the contrapositive can be written as, and I'll put that in, let's see, what color did I not use? Red. This one, we could write, given if P then Q, then I could say conclusion, if not Q, then not P. So sometimes with logical equivalent statements or tautologies, we don't write them across. It does take a lot of space. We write them vertically this way. So we'll review this again. And there's another one that I didn't write, the law of double negation. And what color did I not use? I think I used all my colors. let's see if I have another one. Yeah, and I don't have room here, but I'll summarize it another time. We could say not, if we have not P above, conclude P. Okay, so the laws that we'll see a lot are the ones that I starred: the law of double negation, De Morgan's laws, and the law of the contrapositive. So far, that's what we have. I decided to write the law of double negation here anyway, and just to complete it. So we know that the double negation of P is logically equivalent to P, which its corresponding biconditional is a tautology, but we could write this, which is new. Given the double negation of P, we conclude P. So whatever's below the horizontal line is a conclusion. Every time we would make a conclusion, we draw a horizontal line. But we'll take a look at that more later. Let's take a look at problem number 7 on the sheet, and I'll write it out over here. Okay, in number 7, they ask us to determine whether or not this biconditional is a tautology by making a truth table. And after the truth table, we're asked to answer part B. So let's construct a truth table for this biconditional. And again, we work with the parentheses. We make a column for the left side, a column for the right side, and then finally put it together. And as long as you have a column for everything, but we always begin with the P and the Q. Now, the order of the columns doesn't matter, but it would be good to have the same order since we're doing this together. So we have a not Q column, and I'll put it together: if P, then not Q. Okay, so that takes care of the left side. The right side, I already have a not Q column, but I need a not P column. So we're going to put it together with a not P or not Q. And then finally put it all together. Okay. So let's draw our lines here. And we have true, true, false, false. We have true, false, true, false. Okay, so pause the video, take a minute, and complete the truth table and determine whether or not this statement is a tautology. All right, so I completed some of the truth table for you. The not Q column and the not P columns are easy, but again, remember that a conditional is false when its antecedent is true and its consequent is false. Oh, I circled this wrong one. Okay, let me just erase this. Okay, so let's just do that again. All right. So when the antecedent is true and its consequent is false, then the conditional is false, otherwise it's true. And a disjunction is true most of the time. It's only false when both disjuncts are false. And if you see that, we have two falses here and here. And, wait a second. And actually, that's it. That's the only place we have two falses. This line should be a true. So let me just correct that one here. See, I wasn't very careful here. So that's a true. All right. So now when we look at this truth table, we see that these two columns are exactly the same. So we can conclude that these statements are logically equivalent. We proved two things. But at the same time, we know that false if and only if false is true. True if and only if true is true. True if and only if true is true, and so forth. So this is a tautology. Yes, tautology. And that proves it. So we've proven two things. The biconditional is a tautology, and the two statements are logically equivalent. Okay, again, I don't need parentheses, but I put them there anyway. Okay, now let's look at part B. So now it says, if P represents roses or red, and Q represents violets or blue, what is logically equivalent to roses are not red or violets are not blue? So they're asking us to, oh, this should be not Q. So what would be logically equivalent to not P or not Q? Well, we just proved that not P or not Q is logically equivalent to if P then Q. So I look over here. So I could say, if roses are red, then violets are not blue, is logically equivalent to roses are not red or violets are not blue. And again, because P represents roses or red and Q represents violets or blue, and we translate this in terms of P and Q, well, we're going to use this piece of the tautology. And that's exactly what we said. If roses are red, then violets are not blue. Okay, so that takes care of our lesson. Let's just summarize all of the connectives we've done so far. All right, so we're going to combine all the major connectives in one truth table to reiterate when that compound statement is true or false. So, a conjunction is true when both conjuncts are true. Otherwise, it's false. Whereas a disjunction is false when both disjuncts are false. Otherwise, the disjunction is true. So when at least one disjunct is true, then the disjunction's true. A conditional is false when the antecedent is true and the consequent is false. Otherwise, the conditional is true. And a biconditional is true when P and Q have the matching truth values. Otherwise, the biconditional is false. So note that a conjunction is false most of the time. A disjunction and a conditional are true most of the time. And a biconditional is a 50-50 split. It could be true half the time and false half the time. And that takes care of the summary of our major connectives. All right, everyone, we'll continue the next time. I hope you have a wonderful day. Bye.